unless we actually have colimits. So this idea like push out and is defined. So one nice sort of fact is that in the category of matrices, we also have a factorization system, essentially given by surjections and injections, if you know how to define them for matrices. And then this category we saw last time of linear relations is equal to correlations on this category of matrices that we saw.
Categories, they're equivalent?
Is a field. Okay, we can say they're equivalent if you prefer. But I won't give any details for that. I'm just saying that this is the point is that this is a general concept. This idea of correlations, which we developed in the setting of these wires, is already familiar to us from equivalence relations, but also from these linear relations we saw last time. Okay. So now I want to very quickly tell you about hypergraph categories. Okay, so the idea of a hypergraph category, so this is a rough definition. A hypergraph category is a symmetric monoidal category let's say interpreting wiring diagrams that look like let me draw some wiring diagrams. So what are we allowed to do in hypergraph categories? We're allowed to so remember in a symmetric monoidal category we have these boxes. We can construct new morphisms by taking a morphism which has multiple inputs and multiple outputs and then connecting them up. In the plain symmetric monoidal category we just have to connect sort of inputs to outputs. But in a hypergraph category we have all this sort of graph-like structure which says we can throw out things, we can split things, we can sort of combine things, we can turn things around, we can throw that out, we can initialize something, and so on. So there is a way to axiomatize this by picking out particular structures like we did last time. And that sort of is the sort of usual definition. Well, that is the sort of rigorous definition of a hypergraph category. But I'll just leave you with that picture.
So what is the major difference between this and a signal flow graph then?
What is the main difference between? So a signal flow graph, the category of signal flow graphs is a hypergraph category. But in a general, so a hypergraph category names the structure that signal flow diagrams permit, basically.
I think those had only one kind of wire, and these can have more than one.
Yes, that's true. So I guess a signal flow diagram graph, there's a category of signal flow graphs is in particular a prop, but not all, so you might call it a hypergraph prop, but not all hypergraph categories have to be props. So you actually have genuine objects in the wire. So this is some morphism F from A plus B to C, or A times B to C times D, and so on. Okay. So an example of a hypergraph category is this sort of syntactic category of circuits. And that's, or as I said in the example, any sort of network or circuit-like language that you like. These are all things that sort of are hypergraph categories in the sense that you can see these things and you can understand how people use them, and you realize that the way they're using them can be formalized, that the composition can be formalized using this sort of compositional structure. So what I want to do is show how to construct, say, this category of circuits using, as a hypergraph category, using these ideas about cospans. Okay, so this is the idea of a decorator cospan. And the rough idea, so, is that you might think of, so say we have some circuit diagram. This will really do. You might think of this as some, when we think of this as an open circuit, you start annotating these things you start considering this as sort of a boundary, so some inputs and some outputs or something. So you might consider it as starting with some sort of circuit diagram, which is basically some form of labeled graph, and saying that these things are inputs and outputs. But you might also reverse that and say, we started first with some cospan that said we're allowed to connect things here and here, and actually maybe we're allowed to connect another one there, or allowed to connect something here, and this thing isn't really a terminal. Okay, so it has a point, but it's not really something that's mapped to via from this sort of port, which we're allowed to connect stuff to. And so we have this sort of structure here, a cospan, where this is the inner set, and these are the outer sets. And then we say, we took this cospan and then we put this purple stuff on top. So we decorated this cospan with some extra structure. And the point is, the main theorem is that when you generalize this to a correlational setting with respect to general factorization systems, you can construct every hypergraph category. So anything that has this sort of network language type structure for composition, which includes things like linear relations and special types of linear relations that express properties of sort of certain physical properties. So linear relations that say obey some sort of power minimization condition, whatever that might mean. So you can take these categories and they look very, you're just writing down finite sets or solutions to equations as your morphisms. But because these are hypergraph categories, well, these things can be given the structure of a hypergraph category, and you can construct them using this idea in a general way. But what does it mean? I guess I should tell you, I've given you sort of a picture, but what does it mean to actually have a coherent set of decorating things? And so we need to go back to a structure we sort of hinted at earlier, which is a lax symmetric monodal functor. So a lax symmetric monodal functor takes two categories, or monodal categories, so I call them C times and D times. And then that symmetric monodal functor would be called F, but F is, so what does it do? It's a way of taking one symmetric monodal category and sort of taking all the structure in that and turning it into something, reinterpreting it as a structure in here. So is a functor, so in other words, it takes objects in C to objects in D and morphisms in C to morphisms in D in a way that respects the composition. And then, but it also respects the monoidal structure in what's called a lax way, together with for all objects what does this mean? So to respect this monoidal structure, we want to know that f of n times f of n, so we start with these two objects, n and C, and we want to know that this object and this object sort of cohere, because there are two ways of constructing an object in D out of n and n and C, right? First, we map them both into D, so we get fn and fn, and then we take that tensor product in D, or we take that tensor product first in C, and then we put them through the functor. And so there are various sort of flavors of symmetric monoidal functor that enforce different sorts of coherence between these two objects. So we get some morphisms, which I'm going to call phi and m. And in the lax case, these just need to be morphisms sort of obeying these similar associativity diagrams and things like that, obeying axioms. There are other flavors, for example, a strong one requires this to be an isomorphism, and then a strict one requires it to be equality. So somehow the monoidal product in here is sort of precisely the image of the monoidal product in here, and so on. So there are the different ways of relating lax monoidal symmetric monoidal categories, and we just want the weakest one. Okay. Okay. So here is an example. We take the category of finite sets with the coproduct or the disjoint union as the monoidal product, and we take the category of sets. And so to every finite set, I'm going to give you a set that coheres in a nice way. So we're going to call this C for circuit diagrams. So what we're going to do is on objects, it's going to take a finite set n, say this 4-element set here, to the set of circuits diagrams that exist on n. I won't define that so formally, but the idea is you have some sets here, and you have a set of nodes, and then you can consider sort of labeled finite graph structures or something. But it's labeled by the type of component. Then on morphisms, I'll give an example, which is precisely the sort of spirit of connecting things that we want. If we have some sort of 4-element set, so this is n, this is m, and we have a function from n, sorry, this is n, and we have a function from n to m, then we can take a circuit that lives here and turn it into a circuit that lives down here just by saying, well, this point and this point were connected by a resistor. So now, and this point maps to this point, and this point maps to this point. So now we'll connect those 2 points by the same resistor. That was 1 ohm, now this is 1 ohm. And then this was 2 ohms. And this is going to be the 2 ohm resistor. Right. So this gives us a map from circuits on M to circuits on N. And in fact, you can check this as a functor. You can check it's a monoidal functor by, so we're going to call this map phi the coherence map. So coherence map needs to take circuits on N and our monoidal product here is times. So we have a circuit on n and a circuit on n. And we're just going to map it to a circuit on n plus n. Right, that's exactly this equation here, reinterpreted in this setting. So how do we take a circuit on, so here's my example, how do we take a circuit on 2 elements and another circuit on, we have a circuit on here and a circuit on here. How do we turn it into a circuit on the disjoint union of these two sets? Well, that's really straightforward. We have some circuit. Well, you can just put every point here corresponds to a point over here, so you can just put the same elements between the same 2 points, right? You just literally take the disjoint union of these two finite graphs. So this gives you what's called a lax symmetric monodic functor from this category to this category.
You have 16 minutes.
Cool, that's great. Okay, so now how do I more formally define decorated crisp bands? Well, definition. Firstly, a decorated crisp band, given some lax symmetric monodic functor f, and f decorated crisp band is essentially is a crisp band in C together with crisp band. Here's one crisp band. I'm usually using A and B. Element S in F of n. Okay, so we have a lax symmetric monodic functor which looks like this. A decorated crisp band is a crisp band in the domain category together with, sorry, I was being more specific. It's a lax symmetric monodic functor from some category C with finite colimits. So we can write C plus to set times. So in particular, f of n is an object in here, and maps to an object in here. That's a set.